Hello, in this video I'll talk about a special property of Galois extensions with respect to embeddings in larger fields. So let me start with the Galois extension of my base field K. And imagine that I have a larger field containing E. So what I'm going to prove is that if I look at, informally first, what I'm going to prove is that a Galois extension can sit in effectively one way only in a larger field. So as an up to isomorphism, a subfield in F which is isomorphic to F must be this E. There is no other way of putting it inside F. But I'm going to say it formally here. So I'm going to look at all possible homomorphisms from E into this larger field F. Of course, we'll be fixing the base field K, so homomorphisms will be of algebras or extensions of K. And then naturally, if I look at homomorphisms from E to E, which are inevitably automorphisms, I can compose them, any homomorphism starting in E and going in F. I can precompose with an automorphism of E, and it'd still be a homomorphism going from E to F. And scientifically speaking, this group of symmetries of E acts on the set of homomorphisms. So what I'm going to prove that for a Galois extension E, this action is free, which means that we have as many elements in here as in the group, and the action would just be as if we are looking at the group itself and multiplying. So this is basically the regular action. And alternative way to say that, but it's a slightly less informative way, is to say that these two are in bijection as sets. And the informal statement which I made first is that embeddings as K extensions of E into F is just a one-element set. Just one embedding. So again, what is this notation for embeddings? Embeddings K of E into something larger like F. Well, they are subfields of F isomorphic to E, and isomorphism is supposed to not move around scalars. So isomorphic in some way, we don't really record this way, but if we want to record this way, we will have data of a homomorphism from E into F, an injective homomorphism. But we don't care in the way we really record elements of E, and so we look at this action and we look at the quotient set with respect to this action. So this is an identification of sets. This is really to be set as a definition. Sorry. So that's why if I have a free action, then I just have one orbit, and that's why I just have one element. In this set of embeddings, I just will have effectively one subfield up to isomorphism. So that is just spelling out the definition. Here is the argument. The argument will be very similar to this characterization of Galois extensions via tensor squares of them over the base. So I will be looking now at the tensor product of E and F over the base. So in general, what can I say about it? Well, it's an algebra over F. I can use this component in the tensor product to multiply with scalars from F, thinking of F as the new domain for scalars, and that will make it a commutative algebra over F. And again, by generic feature, it's a tensor product of two separable algebras, so it will have to be separable. Yeah, we'll have to assume that this is separable, so we'll have to assume that this is also Galois. Definitely, but just separable is enough. So it's a tensor product of two separable, hence separable itself. Hence, I can use the Wedderburn decomposition and write it down as a direct sum of simple rings, and they will have to be filled because this is commutative. And again, because it's all this is an algebra over F naturally, so the components in the Wedderburn decomposition will be algebras over F. So let me start with the simplest such algebras, just the field F itself. So I might have, I'm interested in how many copies of F I have in this Wedderburn decomposition. I'm not really interested in anything else, but just F. So the claim is that I can see them by looking at projections from this onto F. So I'm interested really in homomorphisms into F, and the statement is that I'm going to argue is that I'm going to have them at least as many as the number of different homomorphisms from E into F. So that will be at least bounded from below by, because with any homomorphism of a K from E into F, so with any K-linear map, I can construct a thing here. So what I will do is very similar to what was done for the characterization of Galois extensions. I will just take X is from E and Y is from F. It's a shape of a decomposable tensor. So what I can do, I can take X and I can use this homomorphism to turn it into an element in F. And Y is already in F, and I can just multiply them in F. This way I will devise a map, and it's again straightforward to see that this map is a homomorphism. And it is a homomorphism of algebras over F, really. And that is what my direct summands are labeled by in the Wedderburn decomposition. So for any such map, I will have a map of this shape, and for different, I will have different. So that's why I have this bound. Now let's use the condition we have that the extension E is Galois. So if E is Galois, that is equivalent to saying that the tensor product of fields itself over K is in the Wedderburn decomposition is just the direct sum of copies of E, and we know how many copies we will have here. Well, just as many as the number of symmetries. So then let's use this and say something concrete about the Wedderburn decomposition of this. And the trick to use sort of multiplicativity, large multiplicativity of tensor products. So this tensor product I will be doing over E, and that is just replacing F by, replacing E by F. That is extension of scalars, if you like, from E to F. And knowing that this is a direct sum, specifically direct sum of copies of E, I know what to do when I extend scalars in each of those copies from E to F. I will be just seeing direct sum of copies of F. And the number of summons is the same as in here, so this number of summons is the order of the automorphism group. So what I have is the complete answer, not just the partial answer, but the complete answer for the Weissenbaum decomposition, it is all just copies of f, and the number of copies is this, and then we have the number of copies being bounded from below by this, so that makes the action transitive, and that makes the statement true. So that is the argument, and I will stop here.